There's this story that happened in the past few months that probably 99% of us completely missed. And honestly, I don't blame anyone for missing it because it sounds like something straight out of science fiction. But it's real, and it's going to change everything. Picture this. There's a math problem so hard that humanity has been trying to solve it for 150 years. Not 15 years, not 50 years. 150 years. We're talking about some of the brightest minds in history throwing everything they had at this thing and coming up empty-handed. The problem is so notorious that it's one of the 7 Millennium Prize Problems, where solving just one gets you $1 million. That's how impossible these problems seem. But here's the kicker. An AI just did it and not just solved it, but uncovered entirely new solutions that human mathematicians had never even dreamed of. Solutions that have already been mathematically verified and confirmed as correct. When I first heard about this, my immediate thought was, this is either the most incredible breakthrough in mathematics or complete nonsense. Turns out, it's the former. Now, before we dive deep into the technical stuff, let me paint you a picture of why this matters to everyone, not just math nerds. Every time you're on a plane feeling it shake from turbulence. Every time you check the weather forecast and wonder why it's sometimes completely wrong. Every time you see smoke rising from a candle in those beautiful, swirling patterns. All of that is connected to what we're about to discuss. The story begins in the 19th century with 2 guys who probably had no idea they were creating one of the most challenging puzzles in human history. Claude Louis Navier, a French engineer, and George Gabriel Stokes, a British mathematician, independently developed a set of equations to describe how fluids move. Sounds simple enough, right? Just describe how water flows, how air moves, how any liquid or gas behaves. What could be so hard about that? Well, turns out, describing fluid motion is like trying to predict the exact path of every single raindrop in a thunderstorm. It's not just complex, it's mind-bendingly, impossibly complex. These aren't your high school algebra equations where you solve for x and call it a day. These are partial differential equations that describe the relationship between pressure, velocity, temperature, and density at every single point in space and time. Think about it this way. When you stir your morning coffee, the liquid doesn't just move in a simple circle. It creates eddies, swirls, tiny whirlpools, and countless microscopic movements that all interact with each other. Now imagine trying to write a mathematical formula that can predict exactly how every molecule of that coffee will move. That's essentially what the Navier-Stokes equations attempt to do, but for any fluid, anywhere, under any conditions. But here's where it gets really interesting and really difficult. These equations have something called singularities, or as mathematicians like to call them, blow-ups. These are points where, mathematically speaking, things like velocity or pressure spike to infinity. Now, obviously, you never see infinite pressure in real life. Your coffee cup doesn't suddenly develop infinite pressure and explode. But mathematically, these infinite values can exist in the equations, and they make solving them incredibly tricky for 150 years. This has been the mathematical equivalent of climbing Mount Everest blindfolded. Some of the greatest minds in history have taken their shot at it. Henri Poincaré, the father of topology and one of the last true mathematical universalists, gave it his best effort. Andrei Kolmogorov, a legend in probability theory and turbulence research, spent years on it. Dozens of Fields Medal winners. Hundreds of brilliant mathematicians. All of them walked away defeated. It's not that these people weren't smart enough. The problem with Navier-Stokes in 3 dimensions is that it's what mathematicians call nonlinear in the most extreme way possible. Small changes in initial conditions can lead to dramatically different outcomes. It's chaos theory on steroids. Every part of the solution affects every other part in ways that make traditional mathematical approaches essentially useless. I remember reading about one mathematician who described working on Navier-Stokes as trying to grab smoke with your bare hands. You think you're getting close to an answer, and then it slips away. You develop a new approach that works for simple cases, and then it completely falls apart when you try to apply it to realistic scenarios. And then, in early 2024, everything changed. DeepMind, the same team behind AlphaGo, AlphaFold, and other AI breakthroughs, decided to take a completely different approach. Instead of trying to solve these equations the way humans had been attempting for over a century, they asked a different question. What if we could teach an AI to understand the fundamental nature of these equations? This is where things get really fascinating from a technological standpoint. They didn't use traditional AI approaches that just learn from massive data sets Instead, they use something called physics-informed neural networks, or PINs. The difference is crucial. Regular AI is like a student who learns by memorizing millions of examples. PINs are like a student who learns the underlying rules of physics and then applies those rules to solve problems. Here's how it works. Every time the AI makes a prediction about how a fluid should behave, it checks that prediction against the actual Navier-Stokes equations. If the prediction violates the laws of physics, the AI adjusts its approach. It's constantly verifying its own work against the fundamental equations, essentially making sure it's not just guessing, but actually understanding the physics. But the real breakthrough wasn't just in the approach. It was in the execution. These researchers pushed their neural networks to what they call machine precision. We're talking about accuracy levels that are almost incomprehensibly precise. To give you a sense of scale, they compared their accuracy to predicting the diameter of Earth and being off by just a few centimeters. That's the level of precision they achieved. And then came the results that shocked the mathematical world. The AI didn't just solve existing versions of the Navier-Stokes equations. It discovered entirely new families of singularities that no human had ever described before. These weren't just computational artifacts or AI hallucinations. They were real, mathematically valid solutions that revealed new aspects of how fluids can behave under extreme conditions. What makes this even more remarkable is that mathematicians from New York University, Brown University, and Stanford independently verified these results. This wasn't a case of trust the AI. It was rigorous mathematical verification that confirmed every single discovery was legitimate. But here's what really gets me excited. The AI found patterns within these discoveries. When fluids blow up in the equations, you can characterize how fast this happens using a parameter called lambda. The DeepMind system noticed that as singularities became more unstable, there was a surprisingly clear pattern when you plotted lambda against what mathematicians call the order of instability. Basically, the number of different ways the solution could deviate from the blowup. This pattern appeared not just in Navier-Stokes, but in related equations like the incompressible porous media equations and the Boussinesq equations. That regularity suggests there might be a whole landscape of undiscovered singularities out there, waiting to be found. It's like discovering that there's a hidden mathematical universe that follows rules we never knew existed. Now you might be wondering, okay, this sounds impressive, but what does it actually mean for real life? The answer is potentially everything. Let's start with aviation. Every time you board a plane, the reason that plane can fly efficiently is because engineers have spent decades trying to understand how air flows over the wings and fuselage, but their understanding has been incomplete. Forced to rely on approximations and simplified models because the full Navier-Stokes equations were unsolvable. With these new insights, we could design aircraft that are 5–10% more fuel efficient. That might not sound like much, but when you consider that global aviation burns about 100 billion gallons of fuel per year, we're talking about saving 5–10 billion gallons annually. That's not just money. That's a massive reduction in carbon emissions and a significant step toward more sustainable air travel. The implications go far beyond just making planes more efficient. Better understanding of airflow could lead to aircraft that experience less turbulence, making flights smoother and safer. It could help design more effective winglets, those little curved extensions at the tips of wings that reduce drag. It could even revolutionize how we think about supersonic flight, potentially making it more practical and less wasteful. Then there's weather forecasting, which is probably where most people will feel the impact most directly. Why is weather prediction sometimes wildly inaccurate? A big part of the reason is that our models don't fully capture the complex fluid dynamics of the atmosphere. Air is a fluid, and when it moves around the planet, it follows the same basic principles described by Navier-Stokes. Current weather models can accurately predict conditions about 3 to 4 days in advance. With better understanding of fluid dynamics, we might extend that to 5 to 7 days with the same level of accuracy for hurricane tracking. This could mean the difference between a well-organized evacuation and a chaotic scramble. For agriculture, it could mean better crop planning and water management. For renewable energy, it could mean more accurate predictions of wind patterns for wind farms. But let's talk about something even more fundamental: climate modeling. Our understanding of how the Earth's climate system works depends heavily on accurately modeling the movement of air and water around the planet, ocean currents, atmospheric circulation, the interaction between different layers of the atmosphere. All of this is governed by fluid dynamics. Better climate models don't just satisfy scientific curiosity. They're essential for making informed decisions about everything from city planning to international climate policy. When politicians and policymakers are making decisions that affect billions of people and trillions of dollars, they need the best possible scientific information. These breakthroughs could significantly improve that information. The medical applications are equally fascinating. Blood is a fluid, and understanding how it flows through our circulatory system is crucial for treating heart disease, designing artificial hearts, and even developing new surgical techniques. The same principles that govern how air flows over an airplane wing also govern how blood flows through your arteries. Better fluid dynamics could lead to more effective treatments for conditions like atherosclerosis, where arteries become blocked. It could help design better artificial heart valves, more effective stents, and even new approaches to treating aneurysms. We're talking about potentially saving millions of lives through better medical devices and treatments. Industrial applications are massive as well. Any industry that deals with moving fluids, which is basically every manufacturing industry, could benefit. Chemical plants could optimize their processes, reducing waste and increasing efficiency. Power plants could improve their cooling systems, making them more efficient and environmentally friendly. Even something as mundane as designing better plumbing systems could save enormous amounts of water and energy. But perhaps the most exciting aspect of this breakthrough isn't the immediate applications. It's what it represents for the future of scientific discovery itself. This is the first time an AI has made a genuine, verifiable contribution to pure mathematics at the highest level. It's not just faster computation or better data analysis, it's actual discovery of new mathematical truths. Yang Jiwang, one of the lead researchers, put it perfectly when he said they had essentially transformed these neural networks from problem-solving tools into discovery engines. That's a profound shift. We're not just using AI to do things we already know how to do faster. We're using it to discover things we never knew were possible. This opens up questions that go to the heart of what mathematics and science really are. Traditionally, mathematical discoveries have come from human insight. Creativity and intuition, mathematicians would develop hunches about what might be true, then work to prove or disprove those hunches through logical reasoning. Now we have AI systems that can explore mathematical landscapes in ways that human minds simply cannot. They can check millions of possibilities, identify subtle patterns that would take humans decades to notice, and propose solutions that no human would ever think to try. But here's the crucial part. Humans are still needed to verify, interpret, and understand what these discoveries mean. The relationship between AI and human mathematicians in this breakthrough is actually a perfect model for what I think the future of scientific research will look like. The AI doesn't replace human mathematicians, it partners with them. The AI is incredibly good at exploration and computation, while humans are essential for interpretation, verification, and connecting discoveries to broader scientific understanding. When I think about this, I'm reminded of other major breakthroughs in recent years. AlphaFold solved the protein folding problem, which had stumped biologists for 50 years. That discovery is already revolutionizing drug development and our understanding of diseases. GPT and other large language models have transformed how we work with information and communicate. But this breakthrough feels different. AlphaFold and language models are solving problems in applied sciences, biology, linguistics, communication. This breakthrough is in pure mathematics, the most abstract and fundamental of sciences. Mathematics is the language in which the laws of physics are written. When you make breakthroughs in mathematics, you're potentially opening doors to understanding the universe itself in new ways. Of course, it's important to acknowledge the challenges and limitations here. The computational requirements for training these kinds of models are enormous. We're talking about costs that can reach millions of dollars and energy consumption that rivals small cities. There are legitimate questions about whether this approach is scalable and sustainable. There's also the reproducibility issue. Can other research groups replicate these results? With traditional mathematics, if you prove a theorem, anyone can follow your proof step by step and verify it. With AI-discovered solutions, the proof is essentially the entire training process of a neural network with millions of parameters. That's much harder for other researchers to reproduce and verify independently. Then there's what I call the black box problem. The AI found these solutions, and mathematicians have verified that they're correct. But do we really understand why they work? In some sense, we're accepting mathematical truths that we discovered through methods we don't fully comprehend. That's philosophically troubling for a field that has always prized understanding above all else. But despite these challenges, I think we're witnessing the beginning of a new era in mathematics and science more broadly. We're entering a period where human creativity and intuition will be augmented by AI's computational power and pattern recognition capabilities in ways we're just starting to explore. Looking at the bigger picture, there are 6 other Millennium Prize problems that remain unsolved. The Riemann hypothesis, which deals with the distribution of prime numbers, the P versus NP problem, which is fundamental to computer science and cryptography, Yang-Mills theory, which is central to our understanding of particle physics. Each of these problems has resisted human efforts for decades or centuries. Will AI be able to crack these problems too? It's certainly possible, and if it does, we might see rapid acceleration in fields ranging from cryptography to quantum physics to number theory. We could be on the verge of a period of mathematical discovery unlike anything in human history. But I want to be clear about something. I don't think AI will replace mathematicians, any more than calculators replaced mathematicians or computers replaced mathematicians. What AI will do is change what mathematicians spend their time on. Instead of getting bogged down in complex calculations that AI can handle, mathematicians will focus more on the creative aspects of their work, asking the right questions, interpreting results, and connecting mathematical discoveries to real-world applications. This pattern is already emerging in other fields. Doctors aren't being replaced by diagnostic AI, but they are spending less time on routine diagnoses and more time on complex cases and patient care. Lawyers aren't being replaced by AI, but they are using AI to handle document review and spend more time on strategy and negotiation. The same thing will happen in mathematics and scientific research for young people considering careers in STEM fields. This breakthrough offers both challenges and opportunities. The challenge is that the bar for mathematical research is getting higher. You can't just be good at solving equations anymore. You need to understand how to work with AI tools, how to interpret AI-generated results, and how to ask questions that AI can't answer on its own. But the opportunity is enormous. We're entering a period where the pace of scientific discovery could accelerate dramatically. Young researchers who learn to effectively collaborate with AI will be able to tackle problems that previous generations could only dream of solving. They'll be able to explore ideas that were previously computationally impossible and discover things that no human could find alone. The broader implications for society are equally profound. Better weather prediction could save thousands of lives and billions of dollars in disaster preparedness. More efficient transportation could significantly reduce carbon emissions. Improved medical devices could extend and improve millions of lives. More effective industrial processes could reduce waste and environmental impact. But beyond the immediate practical benefits, this breakthrough represents something even more fundamental, proof that AI can be a genuine partner in expanding human knowledge. This isn't just about automation or efficiency, it's about discovery itself. When I think about the history of human knowledge, there have been key moments when new tools opened up entirely, new possibilities for understanding the world. The telescope let us see distant stars and planets. The microscope revealed the cellular basis of life. Computers enabled us to simulate complex systems and analyze vast amounts of data. I believe AI represents the next major leap in our toolkit for understanding the universe. Just as telescopes didn't replace astronomers but enabled them to see farther and discover more, AI won't replace scientists, but will enable them to explore questions that were previously unanswerable. The Navier-Stokes breakthrough is just the beginning. It's proof of concept that AI can make genuine contributions to fundamental science. As these tools become more powerful and more widely available, we're likely to see breakthroughs in fields ranging from physics to chemistry to biology to materials science. But with all this excitement, we also need to be thoughtful about how we develop and deploy these technologies. Vitalik Buterin, the founder of Ethereum, has raised important concerns about ensuring AI development proceeds safely and responsibly. The same tools that can unlock scientific frontiers could also be used in ways we haven't fully considered or prepared for. There are questions about access and equity. If AI-powered scientific discovery becomes the norm, what happens to researchers and institutions that can't afford these computational resources? Could we see a widening gap between AI-enabled science and traditional research approaches? There are also questions about verification and trust, as AI systems become more complex and their reasoning becomes harder for humans to follow. How do we maintain confidence in their discoveries? The mathematical community has been fortunate that the Navier-Stokes results could be independently verified. But that might not always be the case. These concerns are real and important. But I don't think they should overshadow the remarkable achievement we're witnessing for 150 years. The Navier-Stokes problem stood as a monument to the limits of human mathematical ability. It was a reminder that there are some questions so complex that even our best minds, working with our most advanced tools, couldn't answer them. That monument has now fallen. Not because humans became smarter, but because we created tools that could extend our intellectual reach in ways we never imagined possible. We built machines that could think about mathematics in fundamentally different ways from human minds. And those machines discovered truths that had been hiding in plain sight for over a century. The patterns that AI found in these fluid dynamics equations were always there, waiting to be discovered. The singularities it identified were always mathematically valid solutions. But it took a fundamentally different approach, one that no human would have thought to try, to finally uncover them. This raises fascinating questions about the nature of discovery itself. Were these mathematical truths discovered or created? Were they always there waiting to be found? Or did the AI somehow bring them into existence? These might sound like purely philosophical questions, but they have practical implications for how we think about AI's role in science. If mathematical truths are discovered rather than created, then AI is simply a very powerful tool for exploration, like a telescope that can see into mathematical space. But if mathematical truths are in some sense created through the process of discovery, then AI might be genuinely creative in ways we're still learning to understand. I suspect the answer is somewhere in between. The mathematical structure underlying these discoveries was always there, but it took genuine creativity, whether human or artificial, to find the right way to look at it. The AI didn't just stumble upon these solutions through brute force computation. It had to develop something analogous to mathematical intuition to know where to look and how to recognize promising approaches. This brings us to perhaps the most profound question raised by this breakthrough. What does it mean for AI to understand mathematics? When the system found these new singularities, did it understand them in any meaningful sense? Or was it just following computational procedures that happened to produce correct results? I think this question is similar to asking whether a calculator understands arithmetic. In one sense, clearly not. A calculator is just executing programmed procedures. But in another sense, a calculator can perform arithmetic operations correctly and consistently, which is a form of mathematical understanding, even if it's very different from human understanding. The AI systems that solved Navier-Stokes are obviously much more sophisticated than calculators, but the basic question remains: what exactly does it mean to understand mathematics? And can machines achieve this understanding? I suspect we'll be grappling with this question for years to come as AI becomes more capable and takes on increasingly complex scientific challenges. What I find most exciting about all of this is that we're just at the beginning. The techniques that DeepMind used for Navier-Stokes are general approaches that could potentially be applied to other unsolved problems in mathematics and physics. We might see rapid progress on problems that have been stuck for decades, but more than that, this breakthrough suggests that we're entering a new mode of scientific discovery where human creativity and AI capabilities combine in ways that neither could achieve alone. Humans bring intuition, creativity, and the ability to ask meaningful questions. AI brings computational power, pattern recognition, and the ability to explore vast solution spaces. The combination is proving to be more powerful than either approach alone. This isn't human versus machine, it's human with machine, working together to push the boundaries of knowledge further than ever before. As I think about what this means for the future, I'm both excited and humbled. Excited because we're clearly on the verge of a period of unprecedented scientific discovery. Humbled because we're dealing with tools and capabilities that are advancing faster than our ability to fully understand their implications. The 19th century mathematicians who first wrote down the Navier-Stokes equations could never have imagined that they would one day be solved by an artificial intelligence. Similarly, I suspect we can barely imagine what the next generation of AI-powered scientific discoveries will look like. But one thing seems certain. We're living through a historical moment where the nature of discovery itself is changing. The boundary between what's possible and what's impossible is being redrawn, not just in mathematics but across all of science. A century and a half ago, the Navier-Stokes equations represented the outer limit of human mathematical ambition. A beautiful, elegant description of natural phenomena that seemed forever beyond our ability to fully solve. Today, those same equations are a playground for machine learning algorithms. That transformation from impossible to routine captures something essential about the moment we're living through. We're witnessing the emergence of tools that can extend human capability in ways that seem almost magical. But they're not magic. They're the result of decades of patient work in computer science, mathematics, and engineering, building on centuries of human knowledge and discovery. The story of AI solving Navier-Stokes is ultimately a human story. It's the story of human curiosity driving us to ask difficult questions, human creativity finding new ways to approach old problems, and human collaboration, bringing together insights from multiple fields to achieve something that no individual or traditional approach could accomplish. As we stand at this inflection point, looking toward a future where AI and human intelligence work together to unlock the secrets of the universe, I can't help but feel optimistic. Yes, there are challenges and risks to navigate. Yes, there are important questions about how to develop these technologies responsibly. But the potential for expanding human knowledge and solving problems that have plagued us for generations is extraordinary. The Navier-Stokes breakthrough is just the beginning. It's a proof of concept that shows us what's possible when we combine human insight with artificial intelligence in pursuit of fundamental understanding. And if this is just the beginning, I can hardly wait to see what comes next. After 150 years, we finally have the tools to understand how fluids really behave, but more importantly, we've demonstrated that the age-old human dream of understanding the deepest patterns in nature is not just alive. It's accelerating in ways we never thought possible. The future of discovery has arrived, and it's more exciting than anyone dared to imagine.